Hi again, welcome to part 2. We are going to talk more about our memory, RAM. So just now we already talked in the part 1, right? If you haven't watched the part 1, please go and watch it because you need to know the basic thing first before I can proceed to more detail. So we know it from our memory, right? Memory is essentially a giant sequence of bytes, okay? This is like a byte, a byte, a byte, a byte, a byte. And the byte, right, consists of a bit. Okay? Each byte has a unique address, and then it can make up a lot of parts. It's just like the most simple diagram I show you, so it's more easier to understand. Now, okay, this is a more realistic diagram. Usually, we represent the address, right? We are going to represent it using hexadecimal, okay? So this is just, I'm going to show you what the diagram is going to look like first. Computer memory consists of number of storage locations, or you can call it as cells, okay? Cell, each of which has a unique numeric address. This is the numeric address, okay? Addresses are usually written in hexadecimal. If you don't know what is hexadecimal, right, it's actually base 16, okay? Just now, right, we talked about binary. If binary, right, the base is 2, okay? In binary, we are using base 2. If hexadecimal, we are going to use 16. Hex is 6, deca is 10. So hexadecimal is 16. Diagram is very cute, right? It's using numeric representation. Like you see this letter H, you see X, you see 75.62. In reality, like the number, the letter, what you saw in here is not using this type of readable number. What it is stored as is using binary, okay? This is a more realistic one. Normally it's stored using binary number, okay? This binary number can represent the sign. You will learn more in later lecture. Each storage location, right, got a unique address, like I said just now, got a unique address, and it's usually written in hexadecimal, hexadecimal, base 16, like this one, hexadecimal. Okay, each storage location can contain a fixed number of binary digits. This is base 2. We represent it using binary. Okay, the most common size is 1 byte. 1 byte. Okay, we call it as 1 byte. 1 byte consists of 8 bit. Okay, 8 binary digit, 8 bit. Most computer, right, it groups bytes together into something called as word, WORDS, word. Okay? A computer CPU that is capable of accessing a single byte of memory is said to have byte addressable memory. Okay, I repeat, byte addressable memory. Some CPUs, right, is only capable of accessing a word size group. Okay, a word size group. They are said to have word addressable memory. Okay, I repeat, word addressable memory. If you look at this picture, right, this section of memory contains some data. Each byte, right, has a unique address. Okay, it's a unique address. It is used when the data is transferred to or from the memory cell. Okay, most processors can also move data in word size chunk. Okay, like example, this is a word would consist of 4. On a 32-bit system, right, 4 bytes are grouped together to form a word. Can you see this? 1, 2, 3, 4. Is grouped to form a word. There are two ways to grouping can be done, okay? There are two ways. The system, right, that store the most significant byte of a word in the smallest address and the least significant byte in the largest address are said to be big Endian, okay? Big Endian. So you can see it's this direction, going to this direction. The big Endian interpretation of a region of memory is shown here. And if you look at this diagram, right, it stores the least significant byte in the lowest address and the most significant byte in the highest address. So it's going to be this direction. So this is the difference between big Endian and little Endian. Some processors such as ARM, okay, can be configured as either little Endian or big Endian. The Linux operating system, right, by default, it configures the ARM processor to run in little Endian mode. The memory layout for typical program, right, is actually shown like this, okay? It's shown like this. The program is actually divided into four major parts, 4 major memory regions, or you can call it as 4 major sections. Okay, the programmer, right, it will specify the contents of the text region. Okay, text region and also the data region. The stack and heap segments, right, are defined when the application is loaded for running. The stack and heap, right, it can grow and also can shrink as the program execute, or it means, right, the stack and heap, right, can expand and contract, or expand, contract when the application is running. For the text and data segment, right, the text and data segment is fixed by the compiler, linker, and also the loader. The text section, right, the text section contains the executable instruction. For example, right, you write different functions, then the machinery code, right, is actually stored at the text region, okay? I'm going to show you the example. The text region, right, the text region can actually call as code segment also. Sometimes it's referred as code segment because all the binary code, right, machine understandable code is stored in here. So example, in these code segments, right, there are different functions and it's only read only, okay? It can only be read only. It consists of sequence of functions. Each function is a sequence of machine code instruction. And then, right, each instructions occupy one or more bytes. And the last instruction is the return instruction, okay? While the data, right, the data segments depend on how large the program is and how much static data storage has been declared by the programmer. For example, right, the data can consist of constant, strings, literals, global and static variable. And for the data region, right, can also be called as global storage. Sometimes it's referred as global storage. For this one, right, it's actually writable. It's writable, okay? It's not only read only. It's not read only. It's writable, but it has a fixed size. For example, in this diagram, right, global variable, right, global var, this name, right, global var, this global var, right, is stored in this position. And then there's a count, right, this static declare count, right, is stored at this position. And then you see this one string literal. If this one is enclosed in double quote, right, double quotation, is string literal, then it will be stored in this region, okay? And then we are going to look at the stack. What is stack? Stack is same as what is the name sound, right? If you are talking about the stack, right, it's actually last in, first out. I repeat again, last in, first out. If you go in the last, you go out first. It's called as last in, first out. LIFO, LIFO, LIFO. It is used to store temporary or immediate calculation result, and it can be used to store local variable, except static variables. Okay? Just now I already mentioned static variables, right? Static variables is actually stored in the data region. Okay? We are looking at stack now. If you want to store local variables, right, local variable is stored in the stack. And function parameter, sometime, right, you can store the function parameter in the stack. And also function return location. Example, right, where to jump back, right, when the function finish is stored in the stack. It can grow and shrink over time. As I said just now, it can actually expand. For example, you look at this one, right, in this code, right, integer A, you declare integer A, you declare integer B, right? Then it's going to store in the stack like this. And then when it finish, right, before it enter function f, right, can you see this function f with parameter A and B? Before f, the memory actually content of B, A, and return address. When you enter this line of code, right, f, A, B, right, then what happens? It will have another return address and Z, right, will be stored in this stack. The Z will be stored in the stack. And then, right, after it finish, enter this function. When it exit, right, after the f, right, then it exit the return address, then only it go back remaining this one, remaining the B and A and return address of the stack. So in summary, right, the stack is used to store parameter for functions calls. Okay, if you want to store functions calls, right, the parameter is stored in the stack, and also it store the return address and it store the local variables. Let's look at the heap. The heap, right, is a giant pool of dynamic allocated memory. The heap has no particular fixed size or structure. It has no fixed size or structure. It can expand, okay? It can expand and shrink. It allocated and free as needed by the application. The heap contains variables that are allocated dynamically. In a high-level programming language, right? Storage space, right? When we are looking at the storage space, right, a variable can be allocated in one of the three ways, okay? One of the three. What is the first way? The first way, right, you can allocate the variable statically. The second way, right, you can allocate variable dynamically, okay? Called as dynamically. The third one is automatically, okay? If you want to store the variable as automatically, right, then where did it store? It will store in the stack. Okay? Store in the stack if you want to make it automatically. Statically allocated variables are located from the data section. Okay? Allocated from the data section. I repeat again. Statically allocated variables are allocated from the data section. The storage space is reserved and usually reserved and initialized. While the program is loaded and begin execution, right, the address of statically allocated variable is fixed at the time. Okay? It's fixed already at the time. The program begins running, right? When the program begins to run, right, it cannot be changed already. When the variables is allocated automatically, right, often referred to as local variable. If you say as automatically, right, we mean local variable. Local variables are stored at the stack. Okay, we are going to store it at the stack. The stack pointer is adjusted down to make space for new allocated variable. I repeat again, the stack pointer is adjusted down to make space for the newly allocated variable. The addresses of an automatic variables is always computed as an offset from the stack pointer. Okay, from the stack pointer. I repeat again, the address of an automatic variables is always computed as an offset from the stack pointer. Now let's look at dynamic variable. Dynamic variable are allocated from the heap. Okay, dynamic variable are allocated from the heap. Okay, dynamic variable is allocated from the heap using malloc or new or language dependent equivalent. In C language, right, you commonly saw the malloc, so it will be in this region. Okay, the address of a dynamic variable is always stored in another variable known as pointer. Okay, I repeat again, the address of a dynamic variable is always stored in another variable known as pointer. Okay, I repeat third time, the address of a dynamic variable is always stored in another variable known as pointer, which may be automatic or static variable or even another dynamic variable, which may be an automatic or static variable or even another dynamic variable. The four major sections of the program memory correspond to executable code: statically allocated variable, dynamically allocated variable, and automatically allocated variable. So it's important you know this type of thing, how it works together, so that you can write a more efficient code. For example, you need to know how to write the code so it don't take more RAM and to do tasks more efficiently. Although it is possible to construct a computer capable of perform arithmetic in any base, okay, but it is much cheaper to build on one that works in base 2. It's relatively easy to build an electrical circuit with 2 steps using 2 discrete voltage levels, but much more difficult to build a stable circuit with 10 discrete voltage levels. Therefore, right, modern computers work in base 2, okay, base 2, 0 and 1. Computer data can be viewed as simple bit string. The programmer is responsible for supply interpretation to give meaning to those bit strings. A set of bits can be interpreted as a number, a character, or anything that the programmer chooses. Computer memory can be viewed as a sequence of bytes, okay, a sequence of bytes. Each byte, right, will have a unique address. A running program, right, has 4 regions of memory, okay, 4 regions of memory. One region holds the executable code. The other region, right, will hold 3 different type of variables, okay. The 3 other regions will hold different type of variables.